Okay, so we'll get back to the point. Now we have finished off with the data part and the model part, and next what comes down is basically the control plane of this problem. Okay, now here, not working. So today we are essentially getting into training your basic neural network. Now when we say in terms of training, what it essentially means is how will you do all the mathematical operations in order to change the free parameters, or what we call as weights within a neural network. Okay. Now typically the problem which we were looking in hand was something of this sort, that you are given down a image which has a lot of digits, and say you are looking at only one particular digit at a point of time, and you have a camera which is acquiring the image for this particular digit, and that essentially comes to you in terms of a tensor with zeros and ones over there, where zeros are basically black or the lowest intensity, and ones are white or the highest intensity over there, and these values intermediate are basically some values between 0 and 1. Okay. Now that whole tensor over there needs to be of a fixed size. So over here we were assuming that for a fully connected network to be of 28 cross 28, which gave it 784 elements over there. Now that linearized 784 tensor, which is x, goes into this neural network, and out you get down a probability coming over there. Okay. And then we saw that a simple neuron can be written something like this, that if you have a set of inputs, say over here it's x1, x2, x3, and then I want to predict a particular outcome over there, which is called as p, which is my predictor. Now since this p is predicted, so p hat is what I am using over there, and whatever is the ideal value of that output which should be there, what is desired, is called as p without that hat. So whatever comes out of the neural network or is predicted by a model is given the superscript of a hat, and whichever does not have that hat is basically what my ground truth or direct observation in my data set consists of. Now what you are going to do essentially over here is in a simple perceptron like model, you will have a set of weights associated with each of these inputs. You take another weight called as a bias, and then you sum all of them together, and that itself can be written like this, which essentially is again a linear algebra operation, and then what you do is you have something called as a non-linearity, and you produce this one, and these non-linearities are generally of these forms. So the first one is what is called a sigmoid, the next one is what is called as a tan hyperbolic, and based on, so a sigmoid is something which is limiting that output in a 0 to 1, and tan hyperbolic is something which is limited between -1 and +1. And the whole purpose over here for doing this was such that you have a bounded output. Now irrespective of whatever your input is, your output gets always bounded, and now if you look into a whole system over there, so the output of this one goes into another neuron, because this output is bounded, so that neuron also gets a input which is bounded. So essentially you have a system henceforth which is a bounded input, bounded output, and that makes this system stable as well. Okay. Now for forming a whole neural network, the whole idea was that you have not just one output variable which is predicted, but you have a set of output variables which will now get predicted, and accordingly your weights will also change their nomenclature. And we did see that the way we rewrite these weights is you have two subscripts over there. The second subscript is basically the source from where it is coming. The first subscript is essentially the target where it is going. So it's a target comma source kind of a nomenclature which is used over here, and this whole thing can be written down as one simple linear equation. You can have similarly another neuron over there, and that's going to give you another predictor which is called as p2 hat, and p2 hat can also be similarly written down. Now you keep on continuing like this up to the kth neuron, and accordingly you are going to get down the output coming from there as well. Okay. Now the point is, if you can rewrite all of these, then what you get is that y over here, which is all of these outputs, say these p's which are all of these y's which are over here, they can be stacked down into a column vector, and accordingly your biases can also be stacked down into a column vector, such that your weights over here, these are all row vectors which also get stacked, and as a result this whole stack is what becomes a rectangular matrix over there. Okay, good. Now as a result of this, you can still use the same kind of a matrix equation, except for the fact that your weight over here is no more just a row vector, but now it's a 2D matrix. Your bias becomes a column matrix and not just a scalar value. Your X is still that column matrix itself, there is no difference over there, and then you are able to get this one out. So this essentially boils it down to a simple matrix multiplication problem, and that was what was making our life easier. And we also did see in our coding part over there that these kind of connections and everything is what is also called as a linear connection. So you had a nn dot linear kind of a structure which was written down over there whenever you wanted to use a fully connected neural network. Now, if you come to this part, which is essentially to predict out errors, then what happens is that you will be able to predict an error for every single of them. Okay. So if I have one particular output coming down as P1, which is one pattern which I am trying to predict, similarly I can have P2. Now for your say that digit recognition problem, what these are going to be essentially is that this is the probability of the first class, this is the probability of the second class, like this it keeps on going up to the probability of the kth class. So essentially this is the probability that the number is 0 given a particular input x. The second one, P2 hat, is essentially the probability that the number is 1 given the input is x over there. So this is what you are essentially going to find out. So these become your probabilities. Now the point is that since you have multiple number of predictors, you can find out error for each predictor. So that error can be written something like E1. So E1 is basically say that the digit which goes over there. So in our example we saw that the digit was essentially 5. So now what that would mean is that whichever is the probability corresponding to 5 in my ground truth, that probability is what is 1, set as 1, and all other class probabilities are made as 0. That is what it should be. Now when this neuron is predicting something, it's going to predict a value which may be 1, may not be 1, or it can be something in the range of 0 to 1. Okay. So if my nonlinearity is essentially a sigmoid over here, that output value is necessarily going to be limited between 0 and 1. Now that that output value is limited between 0 and 1, what I am going to do is, so going by this, if this one is say P1 is for class 0, P2 is for class 1, so accordingly P6 is going to be for the number 5. So P6 hat is going to be some predicted value, whereas P6 is going to be 1 for that particular patch. All other values of P1, P2, P3, P4, P5, as well as P7, P8, P9, P10 and P11, they are all going to be equal to 0, whereas the predicted value can be something else. Okay. Now I can essentially find out an error which can be on a scalar basis for each of them, or I might assume that this itself is another tensor or vector or whatever you call, and then I can find out a Euclidean distance over there. Now that Euclidean distance to me is also a simple scalar value. The value does not change, it is just a scalar value. Okay. However, what this would assume over here is that everything is independent of each other, and then that there is a perfect orthogonality condition which is valid between each of them. Otherwise you cannot calculate your Euclidean distance. Okay. Now that I get that, we start with this process which is called as error backpropagation. Now what this purpose does is that you have this set of x's, p's and p hats which are calculated. Now how it happens is that in a data set you have this combination of x1 comma p1, x2 comma p2, x3 comma p3, xn comma pn, this kind of a thing which is given to you. Now what this thing is called is essentially a data set or a ground truth over there. So x1 may be some tensor corresponding to a particular image of a digit over there. So I don't know what it may be. So in our case this may be that digit 5 which we were picking up over there. Okay. Now if that is the case, then P1 over here, and then see that these are all written in boldface, and that would essentially mean that this is a matrix over there. So my x1 is a 2D tensor which can be linearized and formed into a 1D matrix, a column vector. My P accordingly can also be written down as a column vector, and that column vector is going to have 10 elements over there. It's a 10 rows into one column, 10 cross 1 size vector over there. And what it will have is essentially the ground truth. So whichever particular class is present, that is going to have 1, everything else is going to have 0. Okay. Now when I pass it through my neural network, initially I will be getting down some values which may not be exactly what I am desiring over there. So that's what I calculate and keep it over here. Now using this whole table, what I do is I find out this part. So what this does is for every single of these predictions which are going, which are Pn and Pn hat, I'm going to find out the Euclidean distance and sum it over all the possible data points which I have over here. Okay. So that's essentially going to give me something which is called as my cost. Okay. Now that cost is represented in terms of J of W. Now the argument which you see inside this bracket is called as W or weights. That's not X, Y, P or anything else over there. The reason for that, so can somebody reason out like why is J represented in terms of weight and not anything else? Yes. So essentially X and P is fixed. The only thing which will influence P hat is just the weight and nothing else. So essentially over here in this whole equation, though your equation is represented in terms of P and P hat, but then P hat is just dependent on that free variable which is called as W and nothing else. So that's the reason you have this W going as the input parameter to this one. Okay. Now the whole part of what we call as a decision making is to minimize this part, which is I would try to have such a W such that the cost over all possible W's is minimized. So my weights can have different combinations. So if weights are also a real value, then I can have different combinations. If weights are integers, then also I can have different combinations. Now there can be a real large space of combinations of weights which I can obtain, and out of any of these possible combinations, for one of them my cost is going to be the least, the minimum cost condition, and that's the one which I desire over here from a neural network. Now what that would imply is that if this cost is if this cost is minimum, so what is the minimum value in which JW can go to? What is the minimum value of JW? 0. When can JW be 0? So if every value between that summation operation is 0, only in that case it's going to be 0, because this is essentially a Euclidean distance. So that's a squared magnitude distance. So Euclidean distance can be a positive quantity only, 0 or anything greater than 0. It can never be a negative. Okay. Now by that definition, only if these Euclidean distances are all 0, in that case only this can be 0. That's a good thing with a monotonic function. It's a great advantage. Okay. Now that would imply that Pn and Pn hat is basically the same, and that's the whole task of our training or learning over here, that whatever my output prediction, that should be the same as my input prediction, input pattern for the complete data set on which I am training, right? So now if that is the case, you get it, but then how do you achieve is using this classical method which is called as gradient descent. Okay. Now if you look over here, what this equation says is that if I have some sort of an iterative way of solving it out, okay, and I am looking at the k plus 1th iteration, then the weight at k plus 1th iteration is dependent on the weight at kth iteration. From that weight, what you are going to subtract is some weighted derivative of this loss, and the derivative of the loss with respect to the weight at the kth iteration, the second operator. Okay. Now does this equation look very familiar to something you have studied in mathematics for some other purpose? Newton-Raphson's method. Now what was Newton-Raphson's method used for? Yes, so given that you have a polynomial and you don't exactly know where the roots of that equation lies over there, this was one particular way you were finding out the roots. Now what did the roots imply? The roots were just implying that wherever there was a zero crossing. So this was used for finding out that zero crossing. Okay. Now here also that's the whole part. Okay. What I am trying to do essentially is I am trying to make this JW as 0. Right. Now what this would imply is that I will have a polynomial such that the minimum value of the polynomial can go to 0. So finding out the minima point as well as finding out a zero crossing is the same problem over here. And what I am trying to do by whole is that I am trying to go towards 0, but in the best case I am going to get limited somewhere in the minima point, which may be just a value greater than 0, but the minima point cannot be a value lower than 0. It cannot be a negative, at least for this particular kind of a loss function over here. Okay. Now what a physical significance of this one would mean is that del W of JW is essentially the derivative of the loss function with respect to weight. So I can pretty much assume that there is a polynomial where your independent axis or the x-axis is essentially my weight, and my y-axis or the dependent axis is the loss with respect to that weight, j of w, right. Now this j of w can be of some sort like this, okay, or it can be like this as well. So imagine this to be some sort of a parabola. Now this part del w of jw is going to be the slope at any point on that parabola, okay. Now look at this one. If I have a parabola like this, then at any particular point, if I am calculating the slope is basically bending outward from that 0 or that minimum position over there, right. Now my target is to bring that weight closer to that 0. So essentially this minus of del w of jw is a slope which is opposing in that direction. So whether if my parabola is like this, whether I am here or I am here, this minus sign is going to push all the gradients towards this center part over here. However, this eta has a very critical role, and the role of eta is that if your gradient is very high, then it's going to just overshoot and run off somewhere, okay. Or if the gradient is very low, then it's going to take forever long in order to come over there. Now this eta's job is essentially to scale that up, like how fast or how slow, such that I am quite stabilizing over here. So let's take an example, okay. Now if you look at this whole part over here, then what you would see is that as you keep on increasing these epochs over here and you go over this, so this iterator k is also what is called as an epoch, then what happens to j of w is something which like this, okay. So initially it will have a loss. Now you update it, does not necessarily imply that it's going to be at a lower loss. So sometimes it can jump high as well, and then again it keeps on going down, okay. Now let's look at the reason of why that was happening. So initially where I am starting, so what I have on this other graph over here is basically I have my weights w1 and w2, which are two independent axes. So I am assuming that I have a neural network such that there are two weights only, okay. And you can pretty much consider this to be a line fitting equation, y equal to mx plus c. So you have a m and a c, there are two independent variables over there, so that's my w1 and w2. So this becomes a linear neuron, a pretty much linear line equation over there and nothing more. Now here I am doing two parts of this graph. One in this blue axis is essentially over the number of epochs or over that free iterator called as k, as I am changing, how is my weight jw changing. The other one is that as I keep on changing over k, then my w is also modifying, because I get a wk plus 1 from a wk, right. So now that I am doing that, so there would be some movements in this particular space of w1, w2 as well, okay. So what we are doing is, let's start at some random guess, some random point. w1, w2 is initially taken as some random guess, and that's what everybody does. So you start at that point, you will have a value over here and a point over here, okay. And this would be a 3D surface plot, some sort of a 3D plot, okay. Now if you densely connect everything, then that can boil down to a surface as well. Now from there, if I change that, so essentially I have a random guess of w, which is w0. Now from w0, I am going to calculate my j of w. From j of w, I am going to get down my del w of jw. I use that and then I get a wk plus 1, which essentially is w1 for me. So for my first point over here, this I get a point which corresponds over here, okay. Now similarly for the next point, I get another point which corresponds over here. Now this is my change in the blue axis part on the graph. You see a change in jw happening, whereas in the black axis part where you have these red dots, you are basically seeing that point moving in a space created by w1, w2, and you are looking at the height, which is j of w, okay. Now if you keep on doing this over and over again, you would see at the end of the point it reaches some point over here, which is at the minimum. The interesting part is that this kind of a surface would essentially come out. So you can experiment this one. So what you can do is, you can have a set of viewpoints and then you try to fit a line across it, okay. Now you would see that and a very interesting example is, say you take a set of points which are almost circular in terms of its topology, Okay. You can generate random numbers, right? So generate random numbers from a 2D Gaussian which has sigma x and sigma y equal to the same thing. So more or less you will get down a circular cloud over that. Now that you get a circular cloud, try to fit a line equation through this. So what you would see that because you have some randomness over there, so for some values of m and c you will get down the minimum error which will come down on this fit. Okay. But then there would be a lot of such possible combinations in which you will be getting down that minimum error coming down. Now that's essentially what this surface is going to look like. So this surface is, there will be multiple points where you are going to get this minimum error of fit. Now for each of them is valid equally, because you would also see that that minimum error is almost the same value. And at a lot of places you will have a very high error, but that high error place is also not unique. There can be multiple spots over there. Now this kind of a surface is essentially what is called as the cost surface topology. Okay. Now this typically for most problems will look like a egg casket. You have seen a egg carrying casket, right? Paper casket in which people carry eggs. Okay. Now this one looks pretty much like that, and what happens for any kind of this kind of a neural network based problem, you will not essentially have a surface which is a full convex. A full convex surface would have meant that there is one unique minima point and everything else is a non-minima point over there. Okay. As well as you don't have a lot of local minimas or anything, even that is gone out over there. Okay. However, in a practical problem that will not be there. So our assumption of, say if I go back in this equation, our assumption over here is that there is going to be a unique minima, but that is not always guaranteed. However, most problems what they would have by virtue of this surface kind of a thing is that within a region of exploration, with a certain amount of guarantee, you will definitely see that you will be able to reach this minima point over here. Okay. And that's that interesting part which will happen. So what we are trying to do is, by way of scaling that factor called as eta, you are ensuring that when you are changing from here to here, the value of eta, if that is very high, that would have meant that along this vector you are going to go more higher. So that would mean that if this value of eta is high, then it skips from this point. Instead of going over here, it can land somewhere over here. Okay. Now again, if the value of eta is very high, then from there, instead of coming here, it again lands to another point. So sometimes you would see that when you are training your network, instead of getting this kind of a smooth decay curve for your loss functions, you would have a very much jitter going down over there. In fact, we would change the values of eta, and you would see in class that there would be those kind of jitters which come down over there. Now, if you are very carefully modulating these values of eta, then you can ensure that it would always follow this one and then come down. Now is the other side of the case, that which is a suboptimal value of eta, a much lower value of eta, and then what will happen? Now what happens typically over there is, it comes down but it slows very much and then it would come down over there. Now what that would imply is that this graph will be like this, except for the fact that this would be taking a longer amount of time in order to come to that convergence point over there. Okay. So one critical point is definitely to work out on what is your way of assessing that eta, so that you get a guaranteed solution coming in over there. Okay. Now the primary part which we had over here is to calculate that gradient, and that, however, is not a trivial task in any way. Okay. Now say I have this kind of a simple neuron over here. Okay. So the whole set is what looks like this. Now if I try to calculate its gradient, then this gradient can be decomposed using the chain rule. Let's look at one particular point, that the loss is never represented in terms of weight. The loss is represented as a factor of this output P. This P is a factor of this summoned output over there, which is Y, and Y is a factor of W. So essentially, if I really want to calculate my gradient over here, then I will have to find out derivatives for each of them. Otherwise, I will not be able to do it. Yes, right? Now, each of them have a different name. Generally, this first one is what is called as a derivative of the cost function. Because you can pretty much see that what this essentially does is, this is derivative of that JW with respect to the independent parameter which is P. The only independent parameter which goes to JW is P. So it's a derivative of the loss function with respect to the input which goes into the loss function. Okay. The next part is the derivative of the nonlinear transfer function. You have a transfer function over here, a non-linearity, which is mapping down whatever is the output of this summation block to that desired output over here. Now one purpose we saw is that if it is a sigmoid or a tan hyperbolic, then you basically have a bounded output kind of a form over there. Okay. Now as a result of this one, you need to also ensure that this function over here, which is the non-linearity, that is differentiable as well, otherwise this is not going to work. Next is that you need to have a derivative of this linear part of the network too. Yes or no? You need to have that derivative of the linear part of the network, which would mean that this set of equations over here, that linear algebra which you are writing, that also needs to be differentiable. If that operation is not differentiable, then I will not be able to get them. Now this would imply very strictly a certain number of impositions over here. One is that each function which you are defining over here also needs to have a derivative which exists. So if your non-linearity over here is something like a hard cut, greater than 0 equal to 1, less than 0 equal to 0. If that kind of a form which was there in Rosenblatt's perceptron model. Now there will be a problem with this, because there is a non-linearity, there is a non-existence of derivative which happens at x equal to 0. Yes, what about ReLU? ReLU has an interesting part. So what happens in ReLU is, because your input is always a number greater than 0, and throughout the network you are always ensuring that there is a number greater than 0. So you don't get a 0 or less than 0 condition over there. So since I don't have the other side of 0 coming down, so in your range of existence of numbers, you would always have that differentiable. Got the point? So in ReLU, so where is the point of discontinuity in a function? So essentially, if you are calculating the derivative by coming from the left hand side versus coming from the right hand side, and if both the values don't match, then you have a problem. Now for ReLU, you can calculate the derivative only from the right hand side. You cannot calculate it from the left hand side, because by virtue of ReLU, you will never have a number which is less than 0. Your number is going to be 0 or greater than 0. You will never have a number which is less than 0. So essentially, you only have a right hand side derivative. A right hand side derivative exists. And leaky ReLU. So leaky ReLU's point is that that's an approximation. So in leaky ReLU, you would always see that the gradient over there at x equal to 0. So this is what we do in terms of our coding, that you would have a discontinuity, but you model down a discontinuity explicitly. Okay. Yes. The weight can be negative. Yes. Oh no, you are not getting the point. So essentially, these parts over here, when you are doing it. Now, otherwise what I would suggest is just hold on till I get into a full convolutional neural network with ReLU, because then I would show you that there is a condition imposition on what can be your type of inputs. So the type of inputs are not negative numbers, as well as there is an imposition on the type of weights which you can take. And what that ensures is that this summation over there in a CNN which has a ReLU is always a number which is greater than 0. So just hold on. So when we come down to that kind of a model, I will show you that there are very implicit assumptions which are there for every single kind of a model which has been made for training it. And when you are using a data, you will have to condition your data to obey that as well. So we will come to that part, that they are all to do with the data part over there. Okay. I did not get your point. It's not a nonlinearity. So, I mean, this was by definition called as a nonlinearity. So, a ReLU is essentially a linear between the range of 0 to anything greater than 0. And what it does is, for all the negative values, it just makes it 0 so that your minimum value is clipped at 0. So, by chance, if you have some number which is lesser than 0, so that you clip it essentially to 0. That's what it does. Okay. So, we will come to ReLU. Just hold on for some time, because one important part of our whole discussion is around transfer functions itself, how these transfer functions are and how they operate, and there are certain characteristics which are very critical to them. Okay. Now, for any kind of a model which has a lot of these neurons connected one after the other, which is called as a multilayer perceptron, you also need to calculate out this derivative, and there where it gets really more tricky over here. Okay. Now in case of the simple neuron where you have one single layer, it was much easier to calculate. And here we are encountering a point where you will have a number of these layers, one connected after the other. Okay. Now the essential part is that you have this p hat and you have this x over here, but then how do you calculate the derivative over this whole thing? So can you guess, or just think over it for some time? You can scribble and try to find out as well what may be the derivative. I told that there has to be a chain rule essentially, and that's what we found out. But then how do you solve the chain rule over here in this one? Yes. So just expand and write it down. So if you need assistance, let's get back to this. This is what you have for a simple neuron. Now for a multilayer perceptron, what would that be? And you can use these conventions of variables as well. So you can call something like output of the first layer after this linear operation is what is y1, and then this one is p1. Now that goes into the second one, which can be y2 and p2, and then subsequently till the end of it. And then just try to write it down. So let's see. What you can do is assume that you have a dth layer over here. So any one of these layers is what is called as a d, and then the linear part of the output is what is called as yd over there. Now what you would end up getting is that say for this last layer over here, that becomes a derivative of the output with respect to that cost function. Then you have a derivative of this p with respect to whatever was a pre-nonlinearity that summoned over there. Okay, and then you have a derivative of that pre-nonlinearity summoned with respect to the weight over there, which is del yd of del wd. Okay, now if you keep on writing this one, you would see that del yd of del wd is again equal to something like this, where it says z of d minus 1 is essentially whatever corresponds to say that output p. Now here what comes down is that the y part, which was after that summation, is essentially in terms of the weights of the previous input and dot product by whatever was the output. Now if that output, so if this is my d minus 1th layer over here, this has an output which is essentially z of d minus 1. Okay, then that whole derivative can again be described in terms of its own vectors over there, whatever are the point by point. Yeah. So my point is, what I am trying to do over here is that you're not getting. So y is the output. Let's get over here. See, y is the output of this summation. Then you have a nonlinearity and you get p. Now this one for my d minus 1th layer, I am calling it as zd. The output of the last layer is what is called as p. So yeah, after the nonlinear transformation, whatever pre-nonlinearity is y, post-nonlinearity is z in the intermediate part, in my hidden layers. Okay. So now if I go with that, then this is what my expansion would come down. Now this whole expansion to the point of the last layer, which is my earliest most over there, that would essentially lead me to a point which looks like this, which is derivative of that output of the summation with respect to weight, which is equal to x. See what was this one? Y was equal to w into x. So del w of y is equal to x, right? So this is going to be my first initial condition over there. Now if I follow this and I keep on writing, then this whole thing is going to come which looks like this. So what you will have is, in this whole network you will have this output loss which is calculated in terms of derivative of a cost function. Okay, then you will have a lot of these which are essentially derivatives of nonlinearities. Wherever you see del y of p, then del z of y, then del z of y, these kind of things coming down, that is basically my derivative of nonlinearity, because what relates my y to z is essentially the nonlinearity and nothing more. Okay, then over there you would get down part of it which is essentially what is the derivative of my perceptron, which is y with respect to that weight. Okay, and that keeps on going so on and so forth till the end part, where the derivative of the of this y with respect to weight is equal to x itself. Okay, and that is input to the network. Now this combined part, which is derivative of the nonlinear transfer function and derivative of the perceptron model one by one, is what is called as derivative of the network itself. Okay, or nabla net. So now your network needs to be differentiable, your loss function needs to be differentiable, and in order for your network needing to be differentiable, what it would also need is that your nonlinear transfer function is differentiable, and anyways this perceptron model is differentiable because that is just a matrix operation over there and nothing more. So this part anyways is always differentiable. What you would also need is that this part or the nonlinearity needs to be necessarily differentiable. Okay, this complete combination of interleaved differentiables between the nonlinearity and the network, nonlinearity and network, is what is called as the derivative of the network itself. Okay, yeah. you'll have to expand that chain rule. Yes, you keep on coming. Which part of it? No. So look into this part. You mean to say this part over here, right? Now look over here. When you replace this part, then what comes out? So there would be an activation. There would be an see this. You have two parts of it. Okay, something with respect to that weight. Okay. Now that I am doing that differentiable over here, what am I going to do? I will get my input activation over there. Yes or no? Expand that matrix. Okay. Now this is what I would suggest is that you take it as a take home assignment. Okay. And one good place to look into this whole differentiable form is to look into Simon Higgins' book. Okay. Now what you need to do is you will have to stop thinking in terms of scalars. Write this as full matrix expansions. You have a matrix on the output which is dependent on something which comes before it as well. And you are going to take a derivative of that one itself. Got the point? So now keep on taking those derivatives one by one. Then you would see that when you are expanding it on the chain rule, you will have that derivative of multipliers. So when you have a and a b and you are taking a derivative with respect to this product over there, then it is a times of derivative of b plus b times of derivative of a, and then it keeps on going so on and so forth. So you will have an expansion which looks like that. Yeah. The question is like I have this expansion because this is what it will be over there. Yes. Next part is y expand which one? This one. So that's what I am telling. Calculate this one and then you would see what would come out. This weight over here is what weight? That is my weight over all possible weights in the network. So this derivative is essentially, if you calculate del w of jw, then that is del w of the first layer plus del w of the second layer plus del w of the third layer plus del w of the fourth layer. Like this it keeps on going. Now you need to expand over that whole series. Now you would see for some of them it will turn out to be 0. So say derivative of loss of the derivative of output of the dth layer with respect to the weight of the d minus 1th layer. That will not have any impact, that will become 0. But others will still be persistent over there. And then expand this whole part. There is a minimized, so this is the whole minimized form at the end of it. So there would be summations, but they would lose out. So this is an assignment for you guys. Solve it out. Solve it out, you will get it. Now I would release this solution, this detailing at the end of the class, but I am not going to do it now. Because I want you guys to essentially do this whole derivative over there. But solve out that derivative. Because one critical part is you are assuming this W as the weight of the last layer. That is not the case. So if you are going to do it, because every layer is independent, so you will have this derivative as a sum rule over there. Now the moment you have it as a sum rule, you would see that the last layer is what is dependent on all my previous layers. But my first layer's weight is not dependent on the last layers. So now this whole thing will keep on coming to a convergent form. So you will have a summation over a lot of product terms and then keep on adding these with common product elements over there and then see what it comes down to the minimized form. Okay. So that's what it comes down. Now one critical part for this whole thing to exist is that you would need this cost function which needs to be differentiable, otherwise this derivative will not exist. Next part is so if we ask you this simple question, I have two different cost functions. One is my Euclidean norm and other is my L1 norm over there. Now which of them will be valid as cost function for this learning problem? Euclidean, but not the L1 norm over there? No. Look at the point. L1 norm will have a discontinuity at 0. It's not a monotonic function, it's a non-monotonic function. Now this one can only be valid if you have a non-zero argument, if you have a only positive or only a negative. So if your p minus p hat is always positive or p minus p hat is always negative, in that case your L1 norm can work out, because in that case you are forcing that the whole thing is monotonic. But other than that, if p minus p hat is essentially between this minus infinity to plus infinity, then this becomes a non-monotonic function. And that's the whole reason why this derivative cannot be used. Okay. Next is, you need this parts of it which is essentially the nonlinear transfer functions for it to exist. Okay. Now if I have a nonlinear transfer function of these two types, then which one is valid and which is not? It's always positive, that's what I am telling. So what will happen for this one, for say Euclidean loss? Is that derivative existing? That's the point, at x equal to 0. Do you have a derivative existing over the whole space, or do you don't have it existing over the whole space? You have it existing. For this one, do you have it existing over the whole space? At 0 there is a discontinuity, right? So that's the whole point over here, that there is a discontinuity, which means that over the whole space it does not exist. The only time this can exist is when this becomes monotonic, but when this one becomes monotonic, this also becomes monotonic in any case. So if x minus x hat is either always positive or always negative, in that case the square of it is always positive, because that will perfectly hold true, right? Now in either of these cases they will exist. The only time when this will exist and this will not exist is when you have a complete range from minus infinity to plus infinity. Yes, but what will happen is, if you look at this whole point, we were finding out that whole calculation for every single sample point x. Now at any given sample point x you hit a 0, but that does not mean that over all the sample points you are going to hit a 0. Right? Now here you have the next part of it, which is essentially to look with the nonlinear transfer functions. Now which of these will hold true? Which of them is something which is completely differentiable, does not have a nonlinear problem? So the first one, which is what is this kind of a loss this kind of a transfer function called? Sigmoid. But the second one will again have that same problem at z equal to 0. So that's sort of like things which we need to keep in mind when we are designing these networks. Okay. Now when you are trying to train, what would happen essentially is something of this sort. So you have an input which goes into this network. Now what this input does is that it calculates this first linear layer, then does a non-linearity, that there is an output which is generated. That output becomes input to the second layer. It again does the same amount of thing. You have a linear algebra form, which is that matrix multiplication, then you have a non-linearity and you have an output being created. And it keeps on going so on and so forth, and you get your p hat. Okay. Now this whole stage is typically what is called as a forward pass over the whole network. Okay. You have two parts of it. One is called as a forward pass. A forward pass essentially means that given an input you produce an output over there. Now that's anyways always going to be the first step over here. You have a sample, you give that sample onto this model, you get some prediction coming out of it. Okay. Now that we got that prediction coming out of it, what do we do next? Once you had p hat, then what do you find? You find out that loss. Okay. So you need to compute this j over here. Once you compute j, the next part is to compute derivative of j. Okay. Now that you have computed derivative of j, you need to compute derivative of the network. So derivative of j was basically the derivative of the loss function with respect to its input. Now you needed to calculate the derivative of the whole network itself. Now that you have that, from there you will be able to use that and get down del w of jw, where w is over all the complete network. And using that you can use your update rule and get down a new value of k. So w of k plus 1 is equal to w of k minus eta times of del w of jw, that part. Okay. Now essentially when you are doing that, what that would mean is that you are going to expand that whole series and impact every single w which comes down. Okay. Now, and we did look into this. Now if you expand and do that whole differentiation over there, you would see that the last layer would compute something in terms of all the previous layers. The last but one layer will compute everything from the last but one but till the previous layer. So and so on and so forth, it keeps on going. Now that implies that there is an update which is happening from the last layer to the first layer. This kind of an operation is what is called as a backpropagation. So the whole name of backpropagation comes from here, that you are essentially coming in the direction which is opposite to that of in which the direction had flowed. And this whole part is also what is called as a backward operation. For most of your libraries, you would see something which is called as a backward, and a backward operation essentially means that you are updating all the weights in this whole network over there. And what you do is, once you have updated, then you go and check whether your loss is something which has become less than a particular threshold or not. If it has become less than that threshold, then stop it. If it hasn't, then again get back to this step one, which is again forward and keep on doing this whole process. Okay. Now, if this condition is satisfied, that it has been able to meet that minimum error bound which you would desire to have, then you can stop this whole operation over here. You don't need to worry about it. Now this first part is what is called as a forward operation over the network. The second part, where you compute your loss, is what is called as a forward over the criteria. Okay, these loss functions are typically also what are called as criteria. Then the next part, which is you calculate the derivative of this loss, that is called as a backward operation. And in fact, you would find out that across most libraries, a forward operation is what will be defined, and a backward operation can be automatically calculated. And then the way of automatic calculation is, if your forward definition is properly defined, then you will be able to let the machine calculate the derivative, because most of these operators are what are defined. So the derivatives are pre-calculated and stored in a library, and you just write down a backward, which means that it's going to reassemble all the pointers and calculate it back. Okay. Now similarly, you will have this calculation going over the network as well. So a network.backward is essentially derivative of the whole neural network itself. Then you have an update parameter, which is to do this backpropagation step over there, where you are going to update all of these W's across all the layers present over here, and this essentially comes to a closure. That's the point. And this part is what you manually monitor. So either you can keep on printing on the screen and you monitor, or generally you can put down a for loop over here, where you, within this loop, you keep on checking, or do while whatever is your favorite way of doing it. So within a for, you have a fixed number of iterations and a exit criteria, or you can have a while that it keeps on continuing till it's able to satisfy this condition over here. So when we get into writing the codes over there, you will see that how this whole iterator is also set to come down. Now whenever you get into any kind of a learning problem, there are different kinds of learning problems. Okay. Now a class of them are what are called as supervised learning, and another class is what is called as unsupervised learning. Now typically a supervised learning problem is something which is defined like this. So say L is what is your loss function, or over there whatever we call as J. Okay. Now the whole task of a supervised learning is that, given a set of training data points X and Y train, you are going to create a model H such that for any new data point which comes down called as X in your testing data set, you are able to predict a value of Y hat in a way such that the loss between your desired Y and Y hat is minimum. Okay. Now one particular point which you need to remember over here, and this is that example of training a neural network which we were looking at. So in our example, we had those P and P hats. Now those P and P hats over here get replaced by Y and Y hat. And how you were doing the whole purpose is that you had a set given in your training data set, and you were using that in order to solve this whole problem. Now there can be two different ways. Either this X can belong to this training data set and that's typically when you are trying to minimize error over the training data set and come to a closure, or this can come from another data set which is typically called as a held out data set, a held out validation data set or a testing data set. Now in that case, what you are trying to do is you are trying to update the network based on a training data set on a separate set, whereas there is another different set based on which you are independently monitoring the performance of this model which has been created. And by way of doing this, what you are able to do is you are able to get rid of something which is otherwise called as a model overfit. Now look into this point. So if I have some n number of points and my model is somehow able to memorize all the n number of points, then in my training data my error can be made 0. Yes or no? If my model can somehow memorize all x comma y mappings, and that can happen if the total number of parameters in my model is significantly larger than the total number of training samples which I have. Now if I can memorize all of these x comma y mappings, then on this whole data set on which I am evaluating, it's going to give me a 0 error, right? But then in another data sample point which I give, which it has not seen during the training phase, it's not going to give me a 0 error. Over there it will be a non-zero error which comes up, and that's going to be a problem. So now what we can do is, if that data point is taken from some other one, and what I do is I monitor, I don't end this training process until that error comes to 0. Then I will be able to decouple these 2 points over there, right? So that's the whole idea of creating a training data set, a validation data set, and a separate testing data set. A validation data set is what you are internally going to use to set your stopping criteria. You don't stop until the error is minimized on the validation data set. And your updates and everything is what is going to take place on the training data set. Okay. The other problem which you have is essentially what is called as an unsupervised learning problem. Now what this unsupervised learning problem essentially looks into is that you don't have a y given over here, or whatever is that output which you are trying to predict. The job is that you will be maximizing the distance between any given y, a y hat which you have predicted now, and all other y hats which are present over there. So this should be in the same line essentially. So it will be maximize the loss between y hat and y hat complement of y. So y hat complement of y essentially means that there can be multiple possible such y's which can be predicted, and whichever is not belonging to y hat, you are going to maximize the distance between each of them. Now a classical example of this is what is called as clustering. A clustering method essentially does that. So what it tries to do is that you will try to map a given pattern onto a set of clusters, onto one of the cluster which belongs to a set of clusters, in a way such that the distance between this cluster to which this point has been assigned will be maximum to all the other clusters. So if my point goes to the cluster of 5, then the distance of this particular point to a cluster of zeros 1, 2, 3, 4, 6, 7, 8, 9 is going to be the highest. That would also imply that it has the lowest distance to cluster of 5. But then if I put down something like that, it will minimize the cluster distance. That does not necessarily always imply that it is going to always end up in cluster 5, because just above that, so say the distance of this point to the cluster index of cluster 5 is something like 0.01. It may be that to the cluster index of cluster 6, the distance is 0.012. I am still satisfying my minimization criteria, but then that is not maximizing the distance, because I would like that they are as far as possible over there. Now this one criteria would essentially imply that you will be able to maximize that whole part. So if it belongs to this particular class, then it should be very far off from all the other clusters itself. So that kind of a problem in clustering is what is an unsupervised way of solving this one. Now your DNNs can be used for solving both supervised and unsupervised class of problems. Now there is another class of problem which is called as classification versus regression problem. So a bit later on we will get into them as well, where you can see that these can be used for solving classification versus regression problems too. Yeah. See, in simple statement what it would mean is that if y hat is predicted as 5, that it belongs to class 5, okay, then what is complement of y hat with respect to all y's, which is all the other classes, 0, 1, 2, 3, 4, 6, 7, 8, 9, okay. Now what I am trying to do is, if this point belongs to cluster number 5, then the distance of this point to cluster number 5 is going to be minimum, that's good. But I also want to maximize the distance of this point to all the other clusters, so that all the other clusters is y hat complement from y, and I am going to maximize that distance over there and all possible such distances which will come down. So you would randomly initialize a few points to belong to a few clusters, and then you find it out. You need to choose out some cluster centroid. So We'll come into neural clustering, deep neural clustering, and then you would see those examples. So as of now, just try to remember this part, that the objective is to maximize, and we'll come one by one to each of them. Okay. Now there is one very critical issue in terms of what is called as a bias variance challenges which would ever come down. Okay. Now typically what you would see is that in a lot of problems you would have data points coming from one class which is very high and from the others which is very low. Now there that kind of a problem is what is called as a bias problem. The issue which comes down is that generally your network tends to have a very low error for this class and a very high error for this particular class. Okay. And we somehow need to get rid of that one. Okay. Now generally the idea is that you will have an unbiased one, but then unbiased one is also not something which is of a very good point. And if we draw back to our earlier lectures, the first week's lectures, then you remember that I had shown you that what is that model fitting problem. So essentially you can have a quadratic, you can have a cubic, or you can have a linear, and if your samples are less, then you would see that a quadratic, cubic, linear, any of them are going to do a good fit. On top of it, if your samples are very skewed, then the issue comes down that there can be a lot of possible linear lines which comes down over here. Whereas the idea which we typically have is that you have an unbiased and a very high variance in your data set, and what that would mean is that both the classes have equal number of samples which come down, and there is a sufficient amount of spread in the features or patterns across these samples as well, and that's something which we desire at any given point of time. So this is something, an imposition which you have on the data set itself, so that your learning becomes easier or your control problem is solvable over here. So next year when we get into it, so with the actual writing of a code for doing the whole optimization over there, we will get into how do we ensure that this kind of a condition is also present over there. So they can pretty much be ensured. So we'll come down like how we will ensure that those conditions are present, and these conditions are something which are associated with, again, like how will you ensure that your ReLU never gets down to 0. So those conditions can be imposed by coming over here. So when we do the hands-on tutorial tomorrow, then we will get into that part of it. Okay. Now these two are not desired, whereas this one is essentially what is a desired condition for us to go forward. No, high variance is desired, because the moment you have a high variance, you have less number. See, the difference is over here. You can have multiple possible solutions over here, whereas in a high variance case, you have only one possible solution. If the variance of data is high, then your variance of the solution space is low. Now what I am desiring is that the solution space's variance be low, and that can be achieved only when the variance of the data space is high. Now what I don't desire is that the variance of solution space not be high. So bias is essentially, do I have data which belongs to only one class? Majority of data. So you remember in the Bayes equation, we had a prior probability, which was number of samples of one class divided by number of samples of the other class. Now if the prior probability of one particular class is very high, then all of my decisions are going to go in favor of that particular class, right? So that's the whole thing. So I would like to have an unbiased data set, which would essentially mean that all the classes are more or less equally distributed, and that equal distribution would also imply that my data set has the highest entropy in terms of my classes. So there was one particular thing which we did. So if we have n number of classes, then the highest entropy of the class distribution can be log of n to whatever base you are taking. Now if that has to be ensured, then the only way I can ensure is when I have this unbiased one. So whatever we did in Bayes, that whole thing gets taken one-on-one into your neural network, because the only thing you are changing with the neural network is that likelihood function which you had in a Bayes, which was well defined, that whole likelihood function is now getting defined through a neural network itself. There is no other change which happens essentially. Now that you have trained your network, comes the next part, which is called as validation. Now what this means is that somebody gave you data, you had a computer, you wrote down a network, you trained it. Now I want to give it back to somebody to put it into a product. And here comes the problem. Why will you train a network, first and foremost? Do you want to build a product, or you don't want to build a product around it? Yes or no? So how many support that you will train a network if you want to build a product? You can raise your hand. I mean, at least few people in support of it. I love it. Okay. How many of you do not support that? Can raise your hands. One guy. You don't want to build a network. That's also perfectly okay. I mean, I'm one of them who dons a different part of the hat. So when somebody is paying me less and is giving me less amount of time, then I would hard code the whole solution. If somebody pays me more and the problem is complex, only then they pay more, otherwise they don't pay more. Then I would build a network around it. Okay. So, but then in your case as well, you will still need to do this kind of an experiment which is called as a large scale validation. Now what this essentially means is, you created a model. Now this model can be either made out of a network. This may not be a network itself. This may be hard coded. You wrote down your explicit lines of code, like if color is red across 50 pixels and if it is green in the surrounding 20 pixels, then this means something. Say a stop sign or a pass sign, something of that sort. You can pretty much code down. A lot of things are much more reliable when hard coded over there. For each of them, you need to do something where you say that in a lot of data examples over there for which my actual output is known, which the network or the model has not seen while it was getting created, how does it behave? Okay. Now this behavior can somehow be tracked by doing something which is called as a cross validation. Okay. So let's get into what things are done. Now typically in a folded cross validation, what you do is, if you have your training data set, I am going to divide that training data set into k number of subsets. Okay. Now let's take a simple problem where there are two classes only, class 0 and class 1, and I don't know whether this is an unbiased data set or not. So I would assume that there are n0 samples in class 0 and n1 samples in class 1. So if this was unbiased, then n0 equal to n1. If this is biased, then n0 is not equal to n1. If it is significantly biased, then say something n0 is much greater than n1. Any one of these conditions. Okay. Now, if I want to do a k-fold validation, so what I would do is, I would divide this whole thing into k number of subsets. Now, how I do that is pretty simple. So I would create each small set having these, so a training set, in order to have these many number of samples, what you can do is, or what is practically done is, you take your data points by taking a n0 plus n1 divided k number of points. This is what you will take in every single subset over there. So you are essentially going to get k number of unique subsets. So if n0 and n1 is something like created by sampling without resubstitution. So then between say subset 1 and subset 2, there won't be any common points. This is what I want to ensure. Plus on top of that, what I would also like to ensure is that the ratio of the class 0 and class 1 in the first subset is the same as whatever was the ratio of n0 is to n1. To a certain extent, I mean, you cannot always have 1:1 mapping, it's too complicated, but at least somewhat closer to that one. Okay. Now, by doing that, you will be able to create a training set which has these many number of samples. Okay. And that can be done by this whole part, which we were telling. Now, what you are going to do is essentially, you set something which is called as a fold. Now, a fold can vary between 1 to k, because you have k number of such subsets. Now, at any given point of time, say for fold 1, what I am going to do is, I am going to take subset 1 for my validation or my testing, and subset number 2 to k for training. In the next part, what I do is, I take subset 2 for testing, subset 1 and subset 3 to k for my training, and I keep on doing this in a daisy chain fashion or a round robin fashion. Okay. So whatever is the fold number, that is essentially my test set number, and everything else goes into my training set. By doing this, you will be able to see that when you have completed this whole thing, now with that same data set itself, you are able to have k number of different experiments which are created. Right? Now that you have k number of different experiments which were created over here, that is going to help you understand that across this k number of experiments which are done k times, whether you have a significant amount of change in performance which has happened. Now comes the point, why would there be a significant amount of change? If you take a neural network, for every single experiment you are going to have a different starting point. Your weights are going to be randomly initialized. So on that loss function, that egg cascade kind of a thing, every time you are going to be at different point. So your minimum point is different. That is one thing which can vary. Next thing is, independent of your initializations, your whole gradient was dependent on what your input was, because your combination of x was different for every single training data. So obviously that way in which it would come down and where it would land in the minima is also going to be different. Okay. Now what we are trying to find out essentially by doing this is that over a set of such explorations which we have done, is there a large amount of variation which comes, or is there a small amount of variation which comes? Now can somebody tell me, what do you desire in terms of performance when I am doing k number of such experiments over there? Will I desire that there is a large amount of variation, or there is a small amount of variation in its performance? Small. Why do you want to have a small amount of variation in its performance? To have a less error in experiment, then I might say that what I would do is, over k number of such possibilities, I would pick up the model which has the minimum error. Let others have maximum higher errors as well. I will just pick up that model which has a minimum error. Yes, so that's the point. Whether the whole mechanism which you have designed, that is reliable enough. So every time that I start training this model, will it give me almost a similar kind of a performance or not? Now generally what we want is, so when you are trying to build a model for the first time, you would try to see whether my error is coming down to minimum. Okay. But that's the objective of training this network. What we are trying to find out is, if every new network, every time I am training the same network over and over again, will it reliably come to that minimum point or not? That's what I am trying to ensure over here. Yes. No, so see, for every fold, there is a, what did we do over here? For every fold, there is a different subset from where the x's are coming. So the samples which it is seeing is very different in every fold. So second time when I am training the model, I don't have the model preserved from the first time. So every time it's reinitialized. Every time you have a random initialization going on. That's how your point on that JW and W space is going to be a different point over there. Okay. Now the reason for this one is, you go and give this model to someone. There can be two ways. Either you can give a trained model, or you tell like, this is what my architecture consists of, and this is the data set, and this is how we train. If you have given the trained model, they are going to have the same performance. But if you don't give the trained weights, the converging weights over there, and you give only the architecture, then how do you guarantee that the performance, and why will that guy trust you? Okay. Now these are critical when you are building up a complete product, because over there it may not always be possible that you can give a trained weight, because that trained weight itself is that intellectual property. The value is not in the model, the value is in that weight, what was there. That's the most valuable part, because that essentially is the knowledge which has been extracted out of the data. The model, anybody could have designed it. You trained it in some clever way such that you came to the best possible performance over there. That's that knowledge which you are going to give, and that is valued. That's very high valued point over there. So we are just checking out reliability. So that every time you do a random start. Oh, so what it essentially means is that if I have IID data, so by doing this sampling, what you are doing is that every time you are training and testing over all of these k folds is independent and identically distributed. So if I have another independent and identically distributed data, which is not from my data set on which I have trained, and if somebody else is going to train that model, then they are also going to get a performance which is of the same order. Oh, there is a mathematical proof. I mean, there is an IID convergence for k-fold cross-validation. The point is that these are things which go into say statistical guarantees of learning, and that's beyond the coverage for us. So you can search out for something called as statistical guarantees of folded cross validation. There are some conditions which you need to satisfy. One of the primary conditions is that the data needs to be independent and identically distributed, and that these folds are also, the class distribution across folds is also IID, and that you have a high variance and a low bias established over there, and then you will come to this convergence. So this is something from late 80s, 1986, 87, something of that sort. Most likely Journal of Mathematical Statistics or something. So it predates the huge machine learning kind of a thing, but they were doing it for clustering and Bayes kind of problems itself. And it's a usable proof. It's a very generic proof. It does not assume a model intrinsic inside over it. Yeah. Essentially the weights will be very different. The weights are necessarily always going to be different. We will a bit later on the class, I mean somewhere in March or early April, we are going to study about that models which will look very different will still have the same output. So when we get into explainability of models and explainability of the whole functions, then you would see that models can look very different, the weights can be very different, but the outputs will still be the same. So what you do is so there are a lot of ways people do is. One is that I can choose the one which has the minimum validation error, one model, or no, not necessarily. So a general assumption would be that you do a democratic process. So what you do is you take all of them and you take an average of the decision output over there. Now that is something which is called as a multiple instance inferencing. Okay. So when we get into multiple instance inferencing and learning with neural networks, I will get you introduced into what that whole idea is. Now generally that kind of an inference is very stable. Okay. That comes from the point that democracy is a very stable form of governance. May not be the best possible form of governance for everything, but then you also know that it will not have erratic behaviors. It's slow, but it's very stable, which goes down. So over here these networks also become very reliable when you pool all the networks together. So pooling all the networks would mean that you are increasing compute complexity because you are independently computing every single network over there. But what this would guarantee is that every time you are going to have more or less a very reliable performance coming over there. Now when you report a particular network's performance or any model's performance, one critical thing is that you need to see whether this has got biased or it has become unbiased. Okay. You ensure that your data point over here was high variance and unbiased. Okay. But we still need to see whether my network got biased or not. Because one trivial thing can be you have a weight which is called as B0 or the bias, and the bias gets pushed onto a very high value or a very low value, and that can basically shift or skew the whole decision over there. I don't want that to happen. So what we do typically is create this kind of a matrix, a 2x2 matrix for a 2-class problem, which is called as a confusion matrix. Now if you have a 3-class problem, then this becomes a 3x3 matrix, a 4-class problem, or 4x4 matrix. Now for a 2-class problem, what this would have is that, say in my ground truth or my actual y or p whatever was there is a positive class which is class 1 or omega 1, and there is a negative class which is not class 1. Okay. So that's called as my negative. Now when I am predicting it out, for every single sample, either it will be predicted as belonging to the positive class or not belonging to the positive class, which is my negative class. Now accordingly, I can form this whole matrix where the number of samples which were actually positive and got predicted as positive is what is called as true positive. Okay. Number of samples which were actually negative and got predicted as negative is what is called as true negative. Number of samples which were actually positive but got predicted as negative is a false negative, and similarly number of samples which were actually negative but got predicted as positive is called as a false positive. Okay. Now in this matrix you would see that accuracy, which is essentially the number of correct predictions. So the correct predictions are 2 positives and 2 negatives divided by all the total number of samples, which is equal to the sum of all elements in this matrix itself. So that's accuracy within classification framework. Okay. Similarly, you have something called as a sensitivity. And a sensitivity is essentially the total number of true positives which you had divided by this row sum, divided by the total number of actual positives. So what sensitivity is going to give you is that what percentage of samples which were actually positive also got classified as positive. So now if I want to have a system where I want to be very much particular about whether my positives are truly classified as positives or not. Okay. So one example can be when you are trying to build a system which is going to do a disease screening. So say for malaria detection or something. Now your objective is that no patient who has a malaria should be left out with that. So essentially in that case we would need that sensitivity becomes 100%. So that there are no false negative, because if a patient who had malaria, you left that patient as not with a malaria, then that patient is going to die eventually. That's very critical. It's a mission critical thing over there. Okay. Now on the other side of it you have something which is called a specificity. Now specificity is basically the number of true negatives divided by this row sum divided by the total number of negatives over here. Okay. Now what is this going to do? Now this one is ensuring that what percentage of things which were actually negative also get classified as negatives, right? So this specificity is going to help you figure out that whatever was truly a negative is actually completely coming out as negative. Now you can see that if your sensitivity and specificity, both of them are 1, then your accuracy is also going to go to 1. Right. So these can be 1 only when Fn is 0 and Fp is 0, and if Fn and Fp are 0 then this becomes 1 as well. So this is one condition, and this is what we would always desire to achieve over there. However, you will see that in real life that will never happen. That never happens in real life. Okay. Now there comes this whole part which is called as precision. Okay. Precision is some sort of a trade-off. So what it does is that out of everything which is predicted as positive, how many of them were actually positive? Now this is not looking at the ground truth, this is looking at out of all the things which are predicted as positive, how many of them are actually positive. Now precision is a very helpful one in terms of doing an mass validation of a system. So what you do is, you have, say, take this example of malaria screening. You made a system where the person goes into, say, it's a photo booth kind of a thing. You walk through a booth or one of those X-ray kind of a scanners, you walk through the scanner and it will tell you whether you have malaria or you don't have a malaria. Okay. Now the point is, can I do a blood test before I put every person inside over there? Now that becomes very complicated. So why not, instead of that every person who goes through it and is detected as and is predicted to have malaria, for each of them now we do a blood test. Okay. Now if my precision is very high, then it would mean that there won't be any false positives, or essentially none of the people who say every single person who came out as positive through that screening system will also be confirmed to have malaria. But you have a riskier side. The riskier side is all the people you said that they did not have malaria may also end up having malaria. Some of them may have malaria, so you don't know. Okay. They are trade-offs which you will have to come down. So precision has this one. So similarly you have something called as a recall, you have multiple of those matrices which you can, matrix which you can compute out of this 2 cross 2. But a very important part what we use today is what is called as an F-score. Now F-score interestingly is something which is an unbiased estimation of how your system performance is. Okay. So what it does is, it takes into consideration both false positive and false negative, like this one and this one and this one. So it's not looking at the negative cases because that's seriously not of my interest. What I am trying to find out is whether whatever I told as positive is actually positive and anybody I told as negative is not positive over that. That's what I want to do. So here I am sort of forcing this whole system to behave in a way such that it's very much glued towards giving me positives, but then not to the extent that it will generate a lot of false positives. Because see, in the malaria screening case, you can have a system where you tell every person as having malaria. Now one good thing is that you will not miss out on anybody who really has malaria, But there will be a lot of people who did not have malaria and you gave them malaria resistant drugs, malaria treatment drugs, and as a result of that what will happen is the body will grow resistant to it. So next time when they have malaria actually and you give them the drug is not going to respond. So you have this one big problem in the world today which is called as what is antibiotic resistant microbes, right? So essentially where this comes down is because a lot of our food products are stuffed with antibiotics, stuffed with insecticides, pesticides, etc. Plus, I mean, we basically love to have a medicine for every single ailment which we have. Now, as a result of that, what's happening is that the microbes inside our body and in the surroundings, they are also getting resistant to it. And they are evolving. They are evolving to become better and better, but possibly we are not evolving at the rate at which they are evolving. So sometimes, if we are used to taking a lot of drugs, then taking in an actual drug at a point of time, it's not going to have any impact. Now that's a major problem. And that can be taken care of if you have a system which has a very high F score, such that it does not tell that, okay, a lot of people are false positives. I would have to reduce that one as well. Okay. Now, how we report that is in terms of something of this sort, which is called as a receiver operating characteristics. Now this is a very, very important part. Now where this name comes down has a very crazy history. Does anybody know about the history of receiver operating characteristics in this room? Yeah. Okay, in a multi-class classification what you are going to do is, say I have omega 1, omega 2, omega 3, 3 classes. So first I will create this matrix assuming omega 1 is equal to positive. Then omega 2 and omega 3 becomes negative. Then I will create another matrix with omega 2. So essentially my F score, precision, sensitivity, accuracy will be for every class. And then for the whole system I can report my average and variance. So now ROC. Now does anybody know about ROCs? Yeah. No, where did the name come from? See, it's a bit crazy name, right? Receiver operating characteristics, like where is a receiver? We had models, deep neural networks, blah, 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 blah. Where is a receiver? Where is a receiver? Does it ever ring a bell? Like where is that receiver? Okay, so this comes from the era of World War. 1930s and radar. So the receiver over here is essentially a radar screen. So have you seen those World War movies, and then there are operators who look into a circular kind of a screen where you have one line which is rotating continuously and there is a peak, 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 and you see a dot which is coming towards you, right? So that peak, 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 and that white dot which is shining over there, that is essentially some target which is there within a range. Okay. Now the receiver over here is the radar receiver which is getting displayed on that particular screen. Now those spots can be generated by a bird flying or an aeroplane flying or say a flock of birds flying. Okay. Now what would happen is that based on the intensity of whatever you are receiving over there, you will have to tell whether this is positive or negative, whether this is true or not true. So now your positive class is a plane and negative class is everything else. So now you can have your sensitivity, specificity, all of those things brought down over here. Now in fact the term sensitivity, specificity were coined for this purpose itself. So sensitivity is how good are you in telling that a spot which has come up was actually an aeroplane. Specificity was how good are you in discriminating a spot, discriminating all places which did not have a spot and telling that they were not an aeroplane. You have two parts of it. Now in the movie that spot is generally very distinct and bright. In general on a radar screen you have something like a cable pulled out version of TV, old days TV, like it will just be black and white and a lot of spots, speckle spots over there. Okay. Now here what we do in this kind of a curve is you have sensitivity specificity plotted in a way such that the maximum value of specificity is over here, a minimum value of specificity over here, and it keeps up. So this is specificity 0, this is specificity 1, and this is sensitivity 0 and that is sensitivity 1. Okay. Now typically over here what happens is that if you keep on, say I take this probability value and I have a threshold on the probability value. So I say that I will look into probability of class 1, okay. So or the positive class, and then say if my probability of positive class is above 90%, only then I say confirm that this becomes positive class, otherwise I say that it is negative class. So I am not doing a argmax anymore. Okay, there is no argmax between the two probabilities, but I am looking at probability of the positive class and the negative class separately, and I am making a decision. Now if I keep on varying those threshold points based on which I am doing, I would end up getting a curve over here by varying the sensitivity and specificity. Okay. Now this essentially would give me a curve which comes over here, and I can calculate the area under this curve. So if I give you a curve, you can always find out what is the area under this curve. Now a good classifier is something, or a good model is something which has the highest area under curve. So essentially this one is better than this one, and there is a reason for that. Now the best case is when the area is 1. So this will be limited by an area of 1, because this is from 0 to 1, this is from 0 to 1. So the maximum area over here is 1. So value of area is going to be anything which is between 0 and 1. The best one is when I will have something which is exactly 1, which is like this. And what that would mean is that independent of whatever threshold I am going to set, I am going to get the best performance coming over there. So that means that there is a very sharp distinction between positive and negative class, whereas this model does not have it. So by changing these thresholds, I can either be very good, say I am on this threshold, then I am very good on sensitivity, but I am very bad in specificity. Whereas if I am at that point, then I am very good in specificity and very bad in sensitivity. And this was the point. So there is a trade-off between sensitivity and specificity, which needs, and you need to get that taken into consideration as well. Now I will stop at this point. From cost functions we will carry on in the next class. So tomorrow we will get you introduced to these cost functions, and then we will start with the training of our neural network. So please remember to bring your laptops in tomorrow's class as well. Okay. Thank you.